we've seen exponential functions, right? Now we want to look and see if we can figure out a little bit more about them. Can we figure out certain properties of them, their domain, their range, where they're increasing, decreasing, anything about concavity, right? So these examples we've seen already, right? We've, come up with, their behavior as we look at X and Y tables of them. And now I'm just curious, if we were to extend those tables, right? We saw these tables back here. Okay, we don't need to recreate them, but how far back could I extend X? So like how negative can X go and how positive can X go? I think it can go as far as I want it to. Okay, so then that means that the domain here is going to be all real numbers, or written in interval notation, minus infinity to infinity. Okay, and the same is actually true for g of x as well. Okay, and then in terms of the range, okay, I'm thinking about the output. Again, the range is connected to the outputs. What sort of numbers was I getting out? Well, again, I'm looking at the y values. So for 2 to the x, I got, 1/4, 1/2, 1, 2, 4. As I were to continue x in the positive direction, y would just continually get larger. And then in the negative direction, I'd have 1/2, 1/4, 1/8, 1/16, 1/32. But the question is, do I ever get to 0? I don't think so, right? You just keep dividing by 2 effectively, right? And you'll never get to 0. In the same vein, as I look at 1/3 to the x, right? 9, 1, or 9, 3, 1, 1/3, 1/9, 1/27, 1/81, 1/243, etc. In the positive direction, it gets really close to 0, but never actually 0 or negative. And in the negative direction, it would still be positive. So when we talk about range, it's going to extend up to infinity on the upper side for the output, but then the minimum is going to be is really close to 0, but never equal to 0. So that's why I have parentheses there, okay? And we've just finished talking about rational functions, so actually this is going to be super helpful for us. If we get really close to a value but never reach it, we get an asymptote, right? In particular, since the y values are getting close to 0 but never reaching 0, I get a horizontal asymptote at y is equal to 0. I get really close to it but never touch it. Okay, let's see. Were there anything else? Let's see. So we want to talk about increasing and decreasing. So what happened to 2 to the x? I think that one was increasing, but because it would go, 1, 2, 4, 8, 16. But then as I looked at 1/3 to the x, that was, 1, 1/3, 1/9, 1/27. This one was decreasing. Okay. And so what do I notice about increasing and the connection to the function, and decreasing and the connection to the function? Well, that's just is going to be when b is greater than 1, it's going to be increasing. But then if b is a fraction between 0 and 1, then it's going to be decreasing. Okay, and so let's just kind of fill out the information here that we already have. So domain is all real numbers, or minus infinity to infinity. Range is 0 to infinity. If b is greater than 1, then the function is increasing. And if the function is the function's base is between 0 and 1, it is decreasing. Okay, horizontal intercept and y-intercept. Okay. So I'm wondering, so f of 0, this would be the, when x is 0, so this would be the y-intercept, or the vertical. Okay, if I put in 0 in for x, I just get 1, right? 2 to the 0, 1/3 of the 0. This actually never changes. Okay, what about the x-intercept? So if we're trying to solve f of x is equal to 0, so we have 2 to the x is equal to 0, but wait, that can't happen, right? There's a horizontal asymptote there. So actually there's going to be none. There's going to not be any horizontal intercepts, okay? Is DNE, I'm going to say does not exist, DNE, okay? Or you can just do like not applicable. And the vertical intercept is always at 0, 1, okay? And then from a graphical perspective, we're going to see a horizontal asymptote at y is equal to 0. And then in terms of concavity, we'll see this when we talk about the graphs explicitly, but in terms of concavity, is going to be concave up on its domain, entire domain, so all real numbers, and concave down on its domain if certain criteria are satisfied. So it's going to be concave up if b is greater than 1. So actually, whenever it's increasing, it's also concave up, and whenever it's decreasing, it's also going to be concave down. Okay, we'll see that as we look at the basic graphs, but more on those in the next video. So as you take landscape of exponential functions, these are important properties to keep in mind: the domain, their range, increasing, decreasing, intercepts, asymptotes, etc. Now, I will also say these are all only applicable for a base exponential function like b to the x, okay? If we have something other than b to the x, like if we have a transformation of it, then these things get adjusted. We might have to move the asymptote, we might have to move the range, the intercepts, etc. So keep that in mind as you work with different exponential functions.